And good morning, and good afternoon, good evening to wherever you are. So thank you for joining me for this dear. I'd like to thank Medicine first for giving that quick introduction. This is so-called distinguished lecture program. Part of that program, I'm asked to speak. The topic, as you can see, is about multiphase flow measurement and the combustion process monitoring through data-driven modeling. I would like to share my experience with all of you in conducting the research here using this technology. So I know a lot of people working in this, and then it's good to exchange our ideas, experiences like this. Okay, so that's that. Now, in the next 40 minutes, I will introduce the basic methodology. How do we use the data-driven modeling to achieve measurement and monitoring? I use the example I'm quite familiar with, multiphase flow measurement. This measurement quite difficult. It's no simple solution. Hence, data-driven modeling may offer a approach. In the meantime, I will also introduce other applications such as leakage detection. How do we predict NOx emissions from combustion processes? Okay. So artificial intelligence has impact in many areas of our life or work. So we do research development in instrumentation measurement. Artificial intelligence obviously have impact in this area as well. And there's a review article published 2 years ago in IEEE Instrumentation Measurement magazine. I extracted this image, as you can see. They call it applied AI method, which are used in across instrumentation measurement in a diverse range of applications. As you can see, people use different terms. They mean more or less the same thing. Various machine learning or deep learning or evolutionary computation. There's a lot of terms here. They are related one way or another. It is how AI is applied in instrumentation measurement. Okay, so in this topic, I will introduce how AI affected or have helped us to achieve measurement in multiphase flow metering. So to start with, I'd like to introduce this important area of application. It's called air-oil two-phase flow metering. When we talk about flow, normally single phase. Here on this occasion, I'm talking about two-phase. The two-phase here means air-oil. So what is that? What we talk about here? You can see the image here. Something you may see if you cross the ferry. You will see a so-called bunker barge. In fact, it's an oil tank of which supplies fuel for a ferry, like this on the right. So then on the left, the barge is a seller. On the right, the vessel is a buyer marine fuels. Okay, so it's oil. The trouble is when you start the so-called filling process, they don't call it filling, they call it bunkering. When you start the process, very often you get air into the system. Okay, so then all this whole process of bunkering, there are a lot of chances you get air into the oil, but customers buying oil, not air bubbles. Okay, so that's how the bunkering process creates a lot of uncertainties in measurement. If you look at the diagram on the right-hand side, the seller has a flow meter. The buyer also has a flow meter. Each flow meter tells you how much you receive, okay, or you sell. In fact, we have two receipts. One from the buyer, one from the seller. The two receipts never been the same. Okay, there's always debate, a dispute. There's some high-profile legal cases in the marine industry. Okay, and at the bottom, I'll give you an example here. And a typical ferry, if we top up 300 metric tons of marine fuel, marine diesel oil, or heavy fuel oil, imagine plus minus 0.5% uncertainty. That is equivalent to roughly $120,000 financial exposure per ferry per year. Okay, a ferry company can have many ferries. Okay, you see, this can equivalent a lot of money per year, which is uncertain. So we need to monitor or measure oil flow rate accurately. So here's an example to demonstrate what happened during a bunkering process. Okay, so the whole process roughly 1.5 hours. Okay, you can blue line is the flow rate in kilogram per hour. Okay, you see it's steady most time, but initially it's uncertain. And during an ending period, you can see it's go up and down along the place. The blue one is density of oil. Okay, it's constant most time, but at beginning and end, you can see it's uncertain because air get into it. So the black line you can see, which indicate air has got into the system. Okay, so in fact, you got 26.7% duration, which has air bubbles get into the system. So the customer is buying oil, not air. So how do we measure oil in mass accurately? It's a challenge, okay? So then we say, okay, how do you monitor oil accurately in the presence of air bubbles? So ideally, obviously, we want to measure mass flow rate, hence total mass. But most proven fluid measurement techniques, they provide volumetric flow rate, not mass. There are proven flow meters on the market, which are based on radiological and nuclear magnetic resonance principles. They're very expensive and not accessible, certainly not suitable for wide uses across marine or similar sectors. So here's a question. Are there any affordable, accessible solutions? Without complex hardware means it has to be cheap enough so people can afford. So what's the option here? And we say, yeah, let's try data-driven modeling, soft computing or machine learning, more or less same thing here. So we did a quick survey in 2018, that's 4 years ago. And we did a quick search here. There are a lot of research activities going on in the academic community, industrial sectors. You can see on the left, all sorts of sensors has been used. Okay, they're quite cheap, well established, and you can see the method they used for the data-driven modeling. Mostly artificial neural network, SVM, and plus some other more complex ones. And the target you can see air, oil, quite common, air, water, and so on, even gas solid. And this box here, a red box, indicate the papers we published. So my team has been working on this over the past few years, so we have some experience. So okay, our approach is to use Coriolis flow meters, okay, to measure two-phase. In other words, oil which has air bubbles. How does it work? Let's try that. So if you have any idea about the Coriolis flow meter, it's quite straightforward. So the flow comes into the flow tube. So the flow tubes are vibrating due to the excitation of the two metal pieces here through control modules. We have upstream, downstream sensors to pick up the signals. So the two signals, there's a the phase shift, delta t. Okay, so from that, the delta t, we can work out mass flow rate, Q dot. Okay, here's mass flow rate, not volumetric flow rate. In the meantime, we can monitor this oscillation frequency of the tubes. The frequency F, it can be used to determine density, okay, of the liquid. Now, this works very well for single phase flow measurement. I mean, single phase oil or just gas within plus minus 0.1% or even better. So it's independent density measurement that's also helpful. The trouble is in real life, in this case, oil has air bubbles. It's air oil two-phase flow, and errors you get from the meters very large. You still get the reading mass flow rate and the density. They're very large errors. And the question is, can we somehow minimize errors by applying data-driven modeling techniques without modifying the hardware? So because if you modify the hardware, it costs you money, manufacturing implications will likely increase maintenance requirement. So the idea is like this. So we still get this is so-called apparent mass flow rate, the density. We know they are not right, but we have that input anyway. The information is there. We also have temperature, which is embedded in the Coriolis flow meter. We can also include a conventional differential pressure transmitter. It is commonly available. It's not expensive. And that's it. We have data come into data-driven models. So it goes through the modeling process. We can predict mass flow rate. Okay, hopefully this is the correct one, then the fairly accurate one. And hence the total mass. In addition to the measurement, we also have flow information such as density, even gas volume fraction. So how much air bubbles in oil, even impurities in the fluid. Okay, so the trouble is when you have a model is built offline, then you use it for online in situ continuous measurement. So somehow we ideally we need to do in situ training from time to time to enhance the performance of data-driven models, which were established before we do the installation. In our case, we also developing analytical models of gas liquid two-phase flow models. So this information can be incorporated in the modeling. So therefore, again, to enhance performance of data-driven models. So this is like whole methodology, how we deploy data-driven modeling techniques to achieve gas liquid flow measurement. Here's an example to show we assess the technology we developed to measure oil flow rate in the presence of air. This is a 4-inch internal pipe. This is a straight tube Coriolis flow meters. Some Coriolis flow meters, they have curved tubes. This is a straight tube. This again straight tube. This is against air oil test. This is 6-inch pipe, pretty large. This video shows you if we do have air bubbles in oil, you can see what happened. So you got a very long and large air bubble, and we have tiny ones. We are not interested in this distribution. We want to measure accurately mass flow rate of oil. So we have done a lot of work in this. You can see here, so imagine initially when you have a Coriolis flow meter to measure oil flow rate, and you have on x-axis GVF, which means gas volume fraction. Okay, so it's two-phase. So the presence of air bubbles makes flow meter often under-reading, sometimes over-reading. Okay, so by deploying our established data-driven models, you can see the error is reduced quite significantly. Okay, so we have tested the systems with different oils, typical oils, special oils. Okay, so that's for commercial reasons. I'm not able to tell you what on oil exactly. Okay, but the message is there. So the data-driven models have helped us to improve the accuracies of oil flow measurement in the presence of air. So tests with oil always costly, inconvenient, sometimes even high risk. We often do research with air-water flow. You can see in the horizontal pipe, vertical pipe situations, you can see the without deploying the established data-driven models, again, you get the mass flow rate either under reading or over reading. Depends on the liquid flow rate, also depends on the volume fraction, so how much air in the liquid. Okay, so this is the apparent mass flow measurement, which had large errors. So then we can deploy established models to reduce that. So this is the traditional Coriolis flow meter plus data-driven models based on support vector machine alone. You can see the errors is reduced significantly. In most cases, the relative errors within plus minus 1%, 1.5%. Okay, we have published results in this paper 5 years ago. If you are interested, you can refer to this paper. Let's move to the entirely different sector. This is like carbon capture and storage. Okay, CCS. carbon capture storage become increasingly important because we're trying to minimize harmful emissions of CO2 to the atmosphere. We want to capture CO2, as you can see in the diagram. After capture, you transport CO2, hopefully in liquid form, towards storage site, which is the depleted oil or gas field. So we hope CO2 stays there for whatever years, then that's it. So that's the whole idea. The trouble is the CO2 in a transportation pipeline could be in gas form, in other words, gas CO2, could be liquid, could be gas liquid, two-phase mixture, or even supercritical form. So the CO2 flow itself depends on temperature and pressure of the transportation pipeline. So for all the good reasons, we need to measure mass flow rate of CO2. This is mass flow rate, okay, not gas phase. So again, for trading, for accounting, for regulation purposes, okay. So here's an example here. Imagine there's a power plant which emits 20 million tons CO2 per year. If there's a 1% uncertainty, which can result in 20 million euros financial exposure, I can imagine CO2 costs gone up a lot over the past few years. It's roughly almost 100 euros per ton. This is February this year. So that's that. So that makes CO2 flow metering more worthwhile, okay, because of the demand. The trouble with CO2 flow measurement under CCS conditions is that we need a platform. Okay, to establish such a platform, it's not easy. We spend a lot of energy and money to build this. So this is a 1-inch CO2 flow test platform under CCS conditions. So on this test rig, you can create, obviously, gas CO2, liquid CO2, or gas liquid two-phase CO2. Okay, we can also even add impurities into the system to test impact of impurities on the flow measurement and so on. Okay, so we have a weighing method to offer a quite accurate reference for flow meters on the test. Also have master meters, again, for evaluation purposes. So this should give you some idea. I have a video clip to show just a moment, if I can show that. You can see the last one. The idea is very simple. So we fix more or less gas volume fraction, the same quantity of gas CO2. Then we change the flow rate. So it's two-phase. You can see the bubbles here on the top, and low flow rate. Then it's partially stratified. Then the fully turbulent flow. Again, this shows you what happened in the CO2 flow pipelines. The flow regime is this horizontal pipe. Again, we want to measure mass flow rate, okay, without actually quantify this exact flow patterns. So here's a setup. This is the Coriolis flow meter under test. This is the weighing column, which offers our reference. Okay, so that's that. This is the test we conducted on vertical test section. On the left is the errors of mass flow rate from Coriolis flow meter without the data-driven models. On right-hand side, you can, after applying the models, the errors reduced much smaller to mostly plus minus 1.5%. Okay, so this error is quite acceptable to the CCS industry. We can also measure gas volume fraction. Okay, that's within plus minus 10%. So this is the vertical test section. For horizontal one, it's similar. You can see in the origin, the errors go all over the place. So after data-driven modeling, then we can see we improved quite a lot. Again, in most cases, it's plus minus 1.5%. Okay, we have published the results in this paper. Okay, this is in the International Journal of Greenhouse Gas Control. Okay, again, three or 4 years ago. I'm trying to show this video here. You can see it. Apologize, I'm not able to click the video clip here. In fact, it shows you it's a transient process during a startup, like CCS process. Initially, it's gas phase CO2, then have liquid CO2 come from left to right. So what's going on here is in a power industry, the CCS is quite dynamic. So the CO2 flow, you start with gas form, then liquid. So you got a lot of transient process. How do we monitor this? It's not easy. So that's the whole idea. I have that video clip. Unfortunately, can't see it. Can see the mass flow rate step increase, stage 1, step increase, stage 2. And the density can see the change as well. Okay, so this is a transient process. So we want to monitor flow rate of CO2 under such dynamic conditions. Again, we have done a lot of tests. The results are quite encouraging. Again, it's published work. If you are interested, you can refer to these publications. Then move to entirely different sector. This gas solid, we call air solid flow measurement. Same thing here in this pipe. Is a mixture of gas solid. Okay, we want to measure mass flow rate of solid, not air. So we use a circular electrode. We call it electrostatic sensors. Also curved electrode. You can see the arrays. Okay, so that's that. I know plus a difference pressure transducer, because the air in it, so we want to know how the pressure change. Okay, in relation to flow conditions. So and the sensing unit is very different from other multiphase flows here. You can see we have a circular shaped electrode, arc-shaped electrode, and the difference of pressure. So and then we go through a signal processing stage. Then we deploy a neural network, support vector machine, and convolution neural network. So the idea is to get the mass flow rate of solids. Okay, we have been doing this research for some years, all conventional, but we have attempted to use data-driven models to do the same thing, to see if it's better. And this is a test rig in our lab. You can see that particle come in from the right-hand side, go through the test section, eventually going to a suction pump. Okay, you can see the flow meter here. It's a 2-inch pipe. Okay, on the electronics computer, you can see on the left-hand side. And we have tried to use SVM model and the CNN model. On this occasion, both are horizontal test section. So as you can see, the CNN model it outperforms SVM model. You can see the errors is slightly less. Okay, SAM sometimes you can sort of data points go quite far from the reference values. Okay, so that's it. This is the how SVM model and the CNN model performed under gas solid conditions. For vertical test section, similar. We tried against the SVM and the CNN models. So again, the CNN model it performs slightly better. Details of results are published in this RPETM paper. If you're interested, you can refer to that paper. Yeah, we feel quite encouraged actually by the method. Again, we are not the hardware already is there. We done a lot of traditional conventional research, but now we just add models, and the performance is indeed improved. Okay, to some extent. Last bit about leakage. Again, from a process is difficult to capture CO2. Then you go through some 100-kilometer transportation. That CO2 could leak. Okay, so there's a demand. How do we detect any leakage? And they want to also know what's the leakage rate. Okay, sometimes the CO2 pipeline also have impurities, such as nitrogen. Do we know how much impurity in that? So again, we are on the test rig presented earlier. We have this storage column. Then we can weigh the mass, so we have reference. So how much mass loss per unit of time. So I have reference leakage rate. Now we have used this acoustic emission sensors and plus thermometer. We can monitor the leak rate. Here's the setup as the reference column. Here's the actual setup. You can see the acoustic emission sensor, the low cost. We have a temperature sensor. Okay, and that's that. And we can create different leak conditions. We tested the methodology again, just like flow measurement. We deploy data-driven models. We extract features from acoustic emission signals in the time domain, frequency domain. And you can see here, we also incorporate the temperature output, and all this information is combined, it's input to the data-driven models, so we can predict leak rate and even volume fraction of impurities, if any. Here's a typical results. Here you can see the measured leak rate. We have relative areas here. It's quite good, plus minus 3% most cases. Even we achieved quite accurate prediction of nitrogen impurity volume. You can see again, it's surprisingly good. We are still working in this area, so the results to be reported in future. We feel the potential is there. Last bit is about how do we use data-driven models to achieve combustion process monitoring. About 10 years ago, we started to try this approach. We have this EMCCD camera, you can see on the left, plus a spectrometer. Again, that's a small miniature and quite low cost. So we have this radical image which from a combustion burner flame. We have a flame temperature information from the spectrometer information. Again, we extract all the features. Then we fit such feature into data-driven models. So we are able to predict a so-called equivalence ratio. This is an important indicator of the combustion quality. You can see it's quite good prediction here. In the meantime, we can even predict NOx, how much NOx emitted from the combustion process. Again, this is surprisingly good, very basic data-driven models. So that's 10 years ago. And since then, we work on and on this. We're trying to improve sensor, improve data-driven models. In the past 2 or 3 years, we did a lot of tests on industrial scale combustion test plant. It's quite large in scale, very difficult to do, and it costs a lot to do such tests. This is a downwards burner. The burners here, the flame going facing downwards. Okay, on this occasion, we have biomass fuel, and we have tried different fuels here. So you have an imaging system, or you get us the imaging here. This imaging can be used to derive a lot of information for our management purposes. For example, from the images on the top, we can measure temperature profiles. Okay, the temperature profiles have a close correlation with NOx emissions. Okay, so once we have a temperature distribution, we fit such information into data-driven models. Okay, so we use the data set we collected to train the model so we can predict NOx. So then most recently, we have made more progress to apply a so-called CNN models to achieve online deep learning performance. In other words, we not just you develop an offline model, you test it under online conditions. So our idea is to develop a model, also try to retrain the model, okay, by incorporating new data coming. So it's kind of like in situ training. So constant improvement of the models we established earlier. So this is important to maintain the performance of previous trained models under real combustion conditions. Okay, so the data again we obtained very encouraging. The details here is published in, again in this TIM journal. So again, my time is limited here. So if you're interested to study this, this give you some idea how we achieve so-called online deep learning. Okay, by incorporating new data. Finally, so we are working in the same area here. So we're trying to deploy data-driven models to across the whole combustion plant. Now, conventional combustion plant is produce electric power 24/7, non-stop. But now in the motor power industry, they have a very complex power grid, which has a lot energy sources, conventional, renewables, this constant optimization. So the power plant has to be operated in a flexible way. You expect frequent start-stop of a 600 megawatt power plant, or constant load change, 300 megawatt, maybe 400 megawatt, then come back again. And then the fuel is not just one fixed biomass, could be different biomass, could be coal, could be oil. So the fuel diet is constantly changing. All this creates so-called flexible operation conditions. They call that smart power plant. All these variations create demand for measurement, modern measurement systems. How do we make sure the combustion process is optimized constantly, regardless the changes in load, in fuel diet, or start again after a short period of time. So all this it's quite a challenge for people like us, like my team. How do we help the power industries to achieve constant optimization? Okay, so again, we are still working on that. You can see we've deployed imaging systems. There's a whole boiler. Okay, I get a lot of data. The imaging system gives us a lot of data, plus traditional data such as temperature, pressure, what kind of fuel, and this information, and emission data. So the idea is trying to achieve constant optimization despite conditions changed. Okay, that's the whole idea. So results to be reported data in future. Okay. There are all the important questions when we talk about how do we deploy data-driven models in the field of instrumentation measurement. Okay. So is the data model approach really necessary? Do we have to use it? Okay. And question very common every time I give a lecture like this. And sometimes if the measurement problem is quite straightforward, convincing the method good enough, you don't need to use a data-driven model. It's an overkill, in my opinion. But the example I have presented, there's no easy solutions. Okay, so data-driven modeling has helped us to achieve things we can't do in the past, and without too much increase in cost. Okay, so in my opinion, this approach is very good to resolve challenging, difficult measurement problems. If something is easily done through conventional methods such as cross correlation, image correlation, or other method, you don't need to do data modeling. Okay. Another question is, are the models we established under lab conditions transportable from a test rig to a plant? Yes, valid question. I think it depends. If the test rig is able to recreate all the conditions we are going to test in a real plant, that's okay. If not, then that's a different case. So a related question, the third one here, on the data set, we use the trainer model representative of the actual process conditions. If the answer is yes, you're confident the model should perform reasonably well. If you can't answer that question, or if you say your data set you used for your model establishment is not representative of the actual process, the big question mark, your model may not perform properly. Okay, so when you do this research, you need to check if the data set you have is representative of the actual process. If somebody gave you a data set, then it's only like a tiny fraction of very complex process. In that case, data set is not reliable. To validate the performance of a data-driven model, you need to conduct unplanned evaluation if all possible. Just see how good it is under real conditions. Okay, in the field, not in the lab. Okay, I know it's difficult to do, but it's something we have to do. I think this is true for all instrumentation measurement systems. Something works in the lab, it may not work in the real process industry. You need to check it. Okay, For that reason, and in situ training is something you have to do, okay? Especially with flow meters. Flow meters are always difficult. Okay, flow measurement process is not simple, particularly under two-phase, even three-phase flow conditions. In situ training is recommended. Then you say, yeah, how do you do in situ training? Where do you get reference data from? So it depends on the process. Sometimes you are able to obtain reliable references, such as from calculations, from another master meters, which you borrowed, or you hired, okay, or you somehow get the data. So then this data, if you trust it, it can fit into your model. So you could do in situ training. It's possible, okay. So this complementary is recommended. It's also like limitation of data-driven modeling approach. So here's my concluding remarks. So I like to summarize by saying that data-driven models has been deployed successfully. Okay, in some cases, okay, as I have presented, the models we have developed mostly artificial neural networks, support vector machine, say NN, or the variants. Okay, the lot combinations here. They give really good performance. Okay, and our tests so far mostly under lab conditions, industrial scale large facilities. We are still working on this so they can perform, they can be evaluated on real plant conditions. So that's why I say in the third point, further work is required. We can see the potential, but we need to do more work. I can only say I'm familiar with the multiphase flow, combustion process monitoring, or even liquid detection. But the potential is that if you can deploy the same approach in other industrial sectors, why not? I know some are being we are research, but some are still premature. Further work to be done to explore how good it is, this data-driven data model approach for other applications. Okay, so finally, I would like to say thank you to the funding agencies. Without the funding, my team not able to do any research like this. Also, my academic industrial partners, they provide very important input. Without their support, I can't do my work. So that's that. I'd like to thank all my teams. Okay, many of my team members are here today. So to thank their input to this. So again, the contributions to teamwork is really cannot be underestimated. Okay, so that's all from me. So that's it.
Thank you so much. Are there any questions about anything that was shared today? If so, please feel free to put them in the question and answer feature in your Zoom toolbar. Okay, I don't see any questions at this time. So thank you so much for your presentation today, and thank you to everyone that joined. And we hope that you'll, attend future IMS VDL talks and have a great rest.
I wonder if people haven't started or or they have questions, or do we stop here now?
Oh yes, someone just posted a question. Sorry, I didn't see any in the tool. Would you like me to read it, or do you want to open the question and answer feature on your toolbar?
I'm looking at the chat window, but I can see your message, but not.
So it's in the question and answer. So it's in the toolbar with the Q&A.
I beg your pardon. Yeah, I'll stop sharing this first. Okay. I beg your pardon. Yeah. Yeah, I can see it. Yes. Okay. Question from Saba. Yeah, thank you for your encouraging comment. Okay. Yeah, how do you take care of temperature variations? Yes, good question. Also, AE sensor frequency range. Do you need to tune the model to suit pipelines? Yes, good question here. Answer the first one. Yeah, temperature. You imagine temperature always affect a lot measurement systems. Yes, in coriolis flow meter case, the temperature is built in already. So for us, it's an independent input feature. to all the models we developed. Even in the gas solid project, we also have used a temperature sensor. So in fact, when you collect the data set, we have created a range of temperatures. Although the under laboratory conditions, ambient temperature, but we try to lower temperatures to 17, 18 degree and go up to even 30 degree by controlling room ambient conditions. Again, you can argue this will not represent real temperature range. Again, that's why I say if you are not able to recreate that conditions under laboratory conditions, you have to collect data under plant conditions. So you improve the performance of the model. So this is definitely the case. Temperature is important. Acoustic sensor range, yes, indeed. And the frequency range is an important feature of AE sensors. Yeah, we have studied this for the given like leakage or even flow measurement. We have narrowed down to this valid period. You can imagine AE sensors are affected by ambient acoustic signals. So we have selected a range which has like the highest sensitivity and least affected by ambient noise. Okay, it is a trade there. Not around 10 hertz up to kilohertz. So that's the rough range. So this varies depends on so that's that. The module need to be tuned. It again depends on the application you want. Okay, so I hope I have answered your questions, Saba. Okay. Next question is question from Madisala. How do you train the data-driven models in real time? And what is the source of the reference, ground truth measurement? Yes, I think this touches part of the questions as well. I'll try to cover as part of my slides, I said. I'm not sure we can do real-time training. I think we need to do a so-called in situ training. In other words, you install your measurement system or instrument there. It's trained, pre-trained, but you need to collect real data where possible, and you trust the references from independent sources, from our master meters, from calculations, and one way or another. Then you feed this data into the system. That's it. I don't think this is real time, but unless you can do this automatically, that could be real time or near real time. In other words, your measurement system has a built-in in situ training functionality. So this module can incorporate new data, then learn itself. It's possible. Yeah, why not? We and my team, we haven't gone that far yet. Something we could try in future. Okay, this is inevitably this action will increase the complexity of the software, of the measurement system software. But that's it. So yes, give a go. Why not? I think it's possible. And the source of reference I covered already in the ground truth. You need somehow to obtain that. For example, in my own case, we try to measure mass flow rate of pulverized coal or biomass. The power plant operators, they do know reference because they have independent iron meters from time to time. They also know time averaged. They know how many tons per hour. So somehow we can derive reference, which is independent from our model, and that data could be used to enhance performance of the models under real conditions. Okay, and actual conditions where the measurement system are installed. So that's that. Thank you, Mehdi, for that question.